Hi guys, welcome to today's lecture. Today we pause our discussion on inferential statistics for a while and have a review of probability theory, which is an important discipline in mathematics and its application. In the world that we live, countless number of events involve some degree of uncertainty. For instance, can we finish our today's class without any technical interruptions? Or what would be the US dollars and Afghani exchange rate tomorrow? Or will we continue online teaching in the summer semester? Or how much would be the economic consequences of COVID-19 in Afghanistan? Or what would be your final grade for this course? You can think of thousands of other circumstances where the outcome is not known for certain. In order to better manage such situations and take best decisions under uncertainty, we need to quantify the degree of uncertainty. The science that studies uncertainty and tries to quantify the degree of uncertainty is called probability theory. In probability theory, for instance, we try to see how much is the chance of finishing our today's class without any technical disruption, or how much is the likelihood of USD Afghani exchange rate to go up tomorrow, or what is the probability of continuing online classes for the summer. Probability theory is a set of methods that model and analyze uncertainty. It is the branch of mathematics with applications in a lot of other fields. It's important, guys, for us to see what probability theory does. It really deals with uncertainty and tries to quantify uncertainty, and that helps us a lot in making decisions in the situations where we are dealing with. In order to quantify or model the uncertain situations, we first need a theoretical base, the elements of which we are introducing next. The first important concept is random experiment. A random experiment is a process which can be under, of course, the same condition, repeated any number of times we want. And importantly, the result of this random experiment is one of more than one known outcomes, meaning that we know all outcomes of the experiment, but we don't know in certain experiment what would be the outcome. For instance, in tossing a coin, the outcomes can be either head or tails, but before performing the experiment, we don't know whether the coin heads up, tails, or head. Or the experiment of tossing a dice would end up in one of the numbers between 1 to 6, but before performing the experiment of tossing the dice, we really don't know how much would be the outcome. Or taking an exam is an experiment. The possible outcomes are passing or failing, but before taking the exam, we really don't know which outcome would. Going to office is an experiment, and the outcomes are either you arrive on time or late, but before performing the experiment, you really don't know which of these outcomes would occur. Or buying a risky asset would result in profit or losses, but before buying a risky asset, you really don't know whether you make profits or making losses. Starting a business is an experiment that could result in profit or losses. But before doing that business, you really don't know for sure whether your business entails profits or losses. Or observing the time until an internet service provider shuts. You really don't know how much time you have to wait for sure that an ISP would shut. Second important concept is sample space. The sample space, guys, in nature is a set that contains all possible outcomes of an experiment. Sample space is shown by omega. For example, the sample space of the experiment of tossing a coin is a set which contains all possible outcomes of tossing a coin, and that's nothing but a set of H for head and T for tail. Likewise, The sample space of taking an exam, as we said, taking an exam is an experiment. The sample space for this experiment is omega containing two outcomes, because the experiment of taking an exam would either end up in passing or in failing. An event is nothing but any subset of omega, which is the sample space of an experiment. For example, in the experiment of tossing a coin, coming up hit is an event. In the experiment of taking an exam, passing the exam is an event. In the experiment of doing a business, making profit is an event. The probability of an event is the number giving us the likelihood of that event to occur. There are many methods to calculate the probability of an event. Here in this course, we limit ourselves to the method called frequency method. In frequency method, what we are doing is we are calculating the frequency of an event occurring when the corresponding experiment is performed for a large number of times. For example, we toss a fair coin for 1000 times and record the number of times the coin hits edge or hits tail. We can use the sample space in order to compute the probability of equally likely events. Equally likely events are those events the probability of which are the same. For example, in the experiment of tossing a coin, the probability of coming head and coming tails are the same. Therefore, in order to calculate the probability of coming head, it's 1 over 2y, because 1 is the number of hits in the sample space and 2 is the total number of events in the sample space. 1 over 2 is the probability of hits in the experiment of tossing a coin. Uni-event and bi-events. Uni-event is the case where we compute the probability of one event. For example, the probability of heads in the experiment of tossing a coin, probability of making profit in the experiment of doing a business, probability of passing in the experiment of taking an exam, and so on. Consider the experiment of tossing a dice. What is the probability that the dice would head up 3? What is the probability of the dice showing up 6? Or what is the probability of an event that the dice show up in odd number? Or what is the probability of the dice showing up a number which is 5 or less than 5? All of them are events and all of them are the bi-events is the case where we compute the probability of an event considering an additional event. For example, the probability of odd and less than 5 in the experiment of tossing a dice, or the probability of even or 4 again in the experiment of tossing a dice, the probability of rain given the cloudy sky, or the probability of negative COVID-19 test given that one has a high fever. In all of these examples, you could see we have two events involved. For example, here odd is one event, coming up less than 5 is another event in the experiment of tossing dice. Raining is one event and cloudy sky is another event in the experiment of checking weather condition. In the case of bi-events, we are concerned mostly with the following cases. Joint probability is the probability of events A and B to occur at the same time simultaneously. For instance, what is the probability of 4 and greater than 3 in the experiment of tossing a dice? The probability of making profit in 2 investments, or the probability of having fever and negative COVID-19 test. Joint probability is showing by probability A, comma, B. Conditional probability is the probability of one event given that the second event has zero. What is the probability of the number being 4 if we know already that the number is larger than 3? Meaning that we already have the information that the number is larger than 3 in the experiment of tossing a dice. Now we want to know how much is the probability that that number is 4, or how much is the probability of arriving late given that there is a long traffic jam. In order to calculate the conditional probability, we use this formula. Conditional probability of A given B is the probability of A and B joint probability divided by the probability of B. Independent events. Two events are independent if the occurrence of one does not provide any extra information on the probability of occurrence of the second one. Coming tails in the experiment of tossing a coin and heading up an even number in the experiment of tossing a dice are independent because coming T in the experiment of a coin does not provide any kind of information on the probability of an even number to heads up in the experiment of tossing a dice. In other words, the two events A and B are independent if the probability of A given B is the same as the probability of A, meaning that the fact that the event B has occurred does not provide any kind of information on the probability of B. In other words, the fact that the event B has occurred does not provide any extra information on the occurrence or on the probability of the event A. Therefore, probability of A given B is the same as the probability of A. From here, probability of A and B is equal to probability of A times probability of B. And this is the condition for the independent events. In other words, A and B are independent if their joint probability is equal to the product of their probabilities.